Okay, right. So from today onwards for the broadcast, I'm going to try something, Miss Daly. Please, can you check for me whether the sound is okay? Because I'm adding the image to it instead of it being just a podcast. But I'm not going to stand here the whole time and shout into the speaker. So can you please just check the quality of the sound? Okay. Then, for those of you who are still looking for tests, these were under the remarks file in my office. So, still looking for a test. I'll take it back today after lectures. I have some senior students who are willing to be tutors, paid tutors, right? So if you're really struggling with this course and you feel that, oh my, I'm falling off the deep end, I can put you in contact with one of those students. It's the only thing I did about the tutors was I had to look at them and thought, oh, would they be able to do this? You know, so it's not the worst student in the class, it's the better students. Yeah. So you should be okay paying them a bit of money, but it's between the you two. I have nothing to do with it. If you want a tutor, contact me and I'll give you contact details. It was a noise, I said, okay. To reiterate, for tutorial 2, in other words, also how you're going to handle your project, also, you do not have to re-implement the algorithms in the book. They're on the book side, just use them. The idea is not to rewrite quicksort. Well, it's 10 lines anyway. You use the library, it's there. Yeah. The point is, what do you see if you use this code? And then there's one other important thing. With insertion sort, I forgot to mention on page 252, I don't know, maybe it was at the end of the lecture or I just forgot. But this is an important property of insertion sort that I forgot to talk about. Please read page 252 and proposition C. The cute thing with insertion sort, you now remember how it works, right? The cute thing with insertion sort is if you give me an array, an input array, I can immediately count how many exchanges would be required to sort the array without sorting it. And the trick is that you can look at how many inversions there are in the array. Inversion is you take every element and see how many elements are out of place relative to this one. Yes, so for example, if we look at the word example, if we look at the word example, it's already not sorted. It's spelled alphabetically correct, but it's not sorted because the sorting would be A has to go in front, and then E, and then L, M, P, and X. So the inversions count how many characters are out of place. Right, so for example, here we have it. Example is my word, and the word example has 11 inversions. E and A are out of place, the first E and the A, yeah. The X and the A are out of place in the wrong order. So you count those inversions, and what proposition C gives you don't need to know the proof. If you count the number of inversions, you can see how many exchanges I have to make. Yes. Because you only exchange once for everything that's out of place, according to this proposition. Yeah. Sorry about that, I forgot about it. Okay, now we're merging. And now I want to come to what we're supposed to do today is quicksort. If I think selection sort, I think n squared. Yes. Why? I take this thing, I find the minimum in the rest of the array, and I find the minimum in the rest of the array, blah, 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 blah. So I'm going through the array that I want to sort repeatedly. Yes. Insertion sort tries to be more clever in that it compares only two elements next to each other and then decides, do I want to sort it or not? Is it out of place? If so, I just do this little front end of the array that's still there. I'm just going to bubble that value through to the back as well. To the front. Okay? But that buys me a constant. Until the notation, it's twice as fast as selection sort. And then we said, well, what about time-space trade-off? If I waste a bit of space, well, actually, if I double the amount of space that I use, the memory, I can do merge sort. Because I can copy my array to an auxiliary array and then divide the problem into increasingly smaller parts. And when I get to two sorted parts, I can merge them without exchanging by copying to the final array. Okay, so exchanges are expensive, you see, and so merge sort actually does it for us. We get a linear arithmetic. Because recursion, I'm dividing my problem all the time. But we can do better than merge sort in principle. And this is where we come to quicksort. So let me just go back to merge. Let's look again at what merge sort does. We copy the array, and then we sort the left part, the right part, and we, yeah. So let's sort right, merge the two parts. And what does merge do? Well, I have a comparison, and then what I do after each comparison, I compare indices, I compare two array elements in groups, and then I do a copy. Yes, I exchange, I don't exchange, I do an array access to copy. And one sort of thinks that this, I can't do better. But quicksort comes and it also has this idea of increasing the smaller arrays. But the arrays are not simply divided in two. We'll see how the partitioning works with quicksort. I'm not going to partition into two equally sized things. And then it does this tiny little detail that in my inner loop, which does the most work, it's going to remove this sign. the assignment jumps out of the loop. Hey, that's it. So, what does quicksort do? Yeah, so it's a little, quicksort is the outer one. If you, when in doubt, use quicksort. In general, quicksort is the one to use. But there are differences. So you have to be very careful with quicksort. In general, on average, it's the best one to use. But there may be cases where quicksort explodes. So if you give quicksort a random input, we can prove mathematically that we are talking about a linear arithmetic algorithm. If you give quicksort sorted input, it becomes n squared. Oh, bummer. So you have to look at your input and make sure that you won't be in a situation where your array is already mostly sorted, and then I get one or two new people who come in, and new entrants that come in, and I have to sort an almost sorted array again. Then quicksort will not work. For example, class lists. Suppose I get a class list in the beginning of the year, so the first day that registration opens, about half of you register. And then I sort my class list. Right? Now I have it sorted. And now I get about 10 people a day extra, yeah, until the last, 7 last day, I don't know, the last week before registration. And then the registrations tickles in one a day. So quick sorting those would be very inefficient because my array is already sorted. And every now and again, I add one more. Don't use quick sorting. So let's look at the basic algorithm. Again, what we are going to get is I start by calling a recursive sort routine, and then inside the sort routine, basically what I want to do is I want to sort a lower part and an upper part. Yeah, just like with merge sort. But note that I now call a partitioning step before sorting. So with merge sort, we set the partitioning of the array into different parts as trivial. Yeah. I simply divide by 2. I take the lower part and the upper part, and they are of equal size. And then I call my sorts on those. And after that, I merge. Now we change it around. Partitioning is going to be my work. And I first partition until I end up with something that is of size 2, and I sort that. Okay, so the idea there is not difficult, but of course, it's the partitioning that's the thing. So how does the partitioning work in quicksort? Wait. We assume that quicksort gets an array which is randomized. Okay? So even if you give it an array that's already sorted, it first has to randomize it, otherwise it won't. So be very careful with your project, because I want to illustrate, in your project, you have to illustrate to me what quicksort does on an already sorted input. So please comment out that line, the standard random shuffle in your project, so that I can see. Otherwise, the comparison is not. I give a not true in a certain sense. Yeah? So take out that random shuffle in your project code. You must also keep in mind that there is a cost to that random shuffle. So if I have a gazillion entries in my array and I need to shuffle them first, how much does it cost? Is it worth the effort? Would that make quicksort slower than merge sort, for example? Okay, so we assume we have random values. The values in the array are randomized. Yeah. There is no order to them. Unless they're my car. Okay, it's like a box of Smarties or something. Right. And we do this little trick. We say, since the elements in the array are randomized, I'm going to choose a value, and that value in the literature, if you read up on Stack Exchange or Wikipedia or wherever you read any textbooks, this value is called the pivot. The part, what Sedgwick and Wayne call the partitioning item is also sometimes called the pivot. And Virtual takes the array and says, I'm going to divide it at this index. Quicksort tries to be clever by saying, I'm not going to divide the array by looking at the index position where I split. No. I'm going to divide the array by using the value of one of the array elements. And we call that value the pivot. And since the values in the array are randomized, it's come see, come sell what value you choose. So just take A of low. In the partition where I am, just take the first value, not the index, the value, A of low. And then I work with A of low. Because, here's a little Java trick again. A of low, I'm going to put into a variable there, into V, because I'm going to compare just against A of low all the time. So I don't want to do an array access every time I compare. So I store A of low in an item, so that I don't have to do my array accesses all the time. It saves a hell of a lot of time. Okay, right. So now I have V. And then I walk through my array. I walk through my array comparing the other elements against this pivot, this partitioning item V. So let's do it. Here is an example. Actually, if you go through the example, it makes all the sense in the world. This is not a whole array. This is one of the partitions. So I have an I and a J. I have an I and a J. Yes, so this is low and high. And I choose element A of low as my pivot. So in this case, the pivot is K. That is K. And then I walk from the left doing things. And I walk from the right doing things. So A increases this way and J decreases this way. It's a cripple. What's the name else? I stalk. I stalk these things where I want to stalk. Right? Okay. So I look at K, that's my pivot. And what I try to find, oh, this is just my break. Yeah. I want to find where I need to exchange. So R is bigger than K. Right. So that sounds good. And on this side, I want to find values that are less than K. Then I do something to them. So if R is bigger than K, I'm cool. A bigger value must go to the right. The smaller value must jump to the left. So I look for a bigger value than the pivot. I find it. On this side, I look for a value smaller than the pivot. S is bigger than K, O is bigger than K, X is bigger than K, C is less than K. So I found a value on the right-hand side that is less than my pivot. And I found a value on the left-hand side that is bigger than my pivot. So less than, big than, but the bigger than is in the left-hand side and the less than is in the right-hand side, so I want to swap. Yeah. So I exchange. Yeah. So I get the R and the C and I exchange them. Okay. And now I continue. My next element for I is an A. Yeah. But A is less than K, so that's cool. The next one is a T, which is bigger than K. So I've got to stop. This is one of those exchange ones. So where was I here? Here was my last time that I exchanged. Right. So Q is bigger than K, that's cool. M is bigger than K. I is less than K. So now I found a value in the right-hand side, which is less than the pivot, and one on the left-hand side that's bigger than the pivot, so it's small. So you keep on pushing. You come from both sides, looking at the value of the pivot. If there is a value for the pivot, if there is a value in the right-hand side that is less than the pivot, I want to put it here. And if here is the value that is bigger than the pivot, it must go on the right-hand side, so I swap those. Yeah, until I get to the middle. Yeah. If I is high break, if J is low break, if I is equal to J, that's when I reach the middle. I break. And then I do exchange. Now note this interesting thing. With merge sort, as I've said a few minutes ago, merge sort does the exchange inside the inner loop. This thing loops and compares, but does not exchange within the inner loop. So the exchange is not expensive. Yeah, because I don't keep on exchanging all the time. Or with insertion. You know, I have my outer loop, and now I bubble with insertion sort. I bubble the values back all the time. I exchange, lots of times. Over here, I exchange once. So it's very quick, so it's very cheap on this thing. Yeah. Right. And that is how we do it. So work through this by hand. I think working through this example should give you a very good idea of how to quick sort an array. So in the test, I could give you an array and say, please quick sort it. Of course, you have to show me the steps. Otherwise, you just have to sort it down. Very easy marks. Okay, so or I could sort something and then say, well, what is the next step? And so, yeah. Right. Please read page 292 carefully. That gives you the array, the quick sort characteristics. I'm partitioning in place. Remember, merge sort didn't partition in place as it were, because we had to make a copy of the AUX array, stay within bounds, preserving, blah, 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 blah. But the blah, blah, blah is important. It's not going to say. Okay. Note on page 293, the inner loop increments the index, compares, yeah. And the second factor is we use very quickly. So let's get to the maths. And again, this is for test purposes, but by now you should know how these recurrence proofs work. Once you get one, you know how they all work. They all follow the same thing. I write down a bound, lower and upper, I choose an equality. I try to solve this thing by substituting recurrence relations. To solve them, you substitute repeatedly in one of the terms. And there you go. So what we now get is that quicksort uses 2n lin n compares. It's a bit. You either have to believe or go back to your maths every now and again, because they get to an expression and then say, and that is exactly ln n. Right? So if you're mathematically minded, if you're a maths major, go double check. If you really are interested in the maths, and you're a maths major or an applied maths major, look at the blue book. Remember I said there's an additional book, the blue book, also by Sedgwick and Flavier, and they truly do the maths. Over here we just, okay, I'll believe it. Right. So let's look at this proofs. Again, note that we don't say that Cn is exactly the number of compares. We say, let Cn be the average number of compares. Watch out for that one. There's a difference between the number of compares and the average number of compares. Right? So this is a statistical idea. It's the average number of compares. Needed to sort n items. So to sort 0 items or to sort 1 item takes 0 time. That's good. Not 0 time, a 0 number of compares. If I get 1 item, I don't compare anything. Please go through the quicksort code to convince yourself. With an empty array or an array with 1 element, where does quicksort break? Doesn't it do any compare? Just double check. And now we can write the recurrence relation, and the recurrence relation comes exactly from the code. So, wow, okay. Rather long recurrence relation, but let's pull it apart. The first term is the cost of partitioning. And now again, you have to go back to the code and say, why would it take n plus 1 steps to partition? So look at the Java. What does partitioning do? Why is the cost of partitioning at most n plus 1? Might be less. Under what circumstances would it be less? I don't know. Look at the code, convince yourself that those values are correct. The easy way to remember these things is actually go back to the code until you get that gut feeling where it just jumps out of the code. You look at the Java, you look at this, you say, wow, at most n plus 1, for heaven's sake, something else that I have to memorize for this course. But look at the Java, work through an example, and once you get it, you don't have to remember it, because then it just makes good sense. That is if you're serious student, which I think you are, preaching to the converted, attending a lecture at 8 o'clock on a Thursday morning. But then that makes sense, right? Okay. The second term, that's C0 plus C1 plus up to Cn minus 1. So it's the sum of those divided by n. The book claims is the average cost of sorting the left subarray. We're looking at the average number of pairs. Average number of pairs. Can you see that it's an average? Yes, it's simply an average. What is an average? Add them all divided by the number of. So that is an average expression there. Okay? And since I have the third term is the average cost for the right subarray. Again, the same thing. Yes. And now, what I can do is I want to start solving this thing. It's an inequality. Because I started out by saying, let's take the average. So this is the average cost, approximate more. It's not the best cost, it's not the worst cost, it's not always the cost that quicksort will be, because quicksort is dependent on how the input looks. We start out with this average in general, but not necessarily always. Okay, so let's solve this thing, and now it just becomes calculations. I multiply by n because I have all these divide by n's, which I want to get rid of. So nc of n, I is n times n plus 1 plus 2 times that, and subtracting the same equation for n minus 1. So again, it's the same old trick that we use when we use the transformations. I get a certain equation, yes, and then I have C0s and C1s and so on. So what I want to do is I put in n minus 1 as my parameter instead of n. If you put n minus 1 into that thing up there, you get a different equation, yes, but of course it's true. It's a function for x and the same thing for x minus 1. Is everybody happy with that? Yeah. Right. So then they didn't write it out. I suggest you do, just to convince yourself, subtracting the same equation for n minus 1 from this one gives me a new equation, rearrange, divide, yappity yappity yap, I'm just doing arithmetic. Yeah? Rearranging, dividing by n times n plus 1 gives me another one. And now, oops, make sure that you know how to get to that last step. Which telescopes? What do I mean by that? Yeah. So they want to get to Cn, and then they immediately fall into the Tilden notation. Write it out step by step and see whether you can get here. And there's a hint. You've got the something divided by n, something divided by n plus 1 all the time. So over here you get the sum. You divide by n minus 1, so therefore you get this fraction. And you add up all these fractions, so it's a third plus quarter plus blah, 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 which you should know about. It was in section 1.4, that is which series?
Harmonic.
Harmonic, yeah. So this is the harmonic series. And now you have to believe, or go check in the group if you really want to know and not just believe, that if I have the harmonic series there, that is the estimate of the area under the curve 1 upon x from 3 to n plus 1, and that Cn actually is 2n than n. Okay, it's in section 1.4. Algorithms. The table is there about all the handy series that you can do. If I can just find it. Yay! So this is on page 185. There we go. Harmonic numbers, Hn. There we go. Yeah. And then the solution. That's the series, and here is the solution. 1 plus a half plus a third plus a quarter plus 1 upon n is simply ln n. Simply practically first in maths. Or add maths in school. Somewhere it creeps up. Yeah. So believe it or go read up on it, it tickles your fancy. Yeah. And that is quicksort, the analysis of quicksort. This one you must know. Proposition K, Miss Daly, are you writing down? Proposition, the proof of proposition K. Now we get, that was on average 2 and then n compares, but that was the average case. In the worst case, you don't need to know the proof, you can read through it for interest sake. In the worst case, what is the worst case for quicksort again? When the input is sorted already, then we get n squared. And page 296. You can quickly read through page 296 how to do a few Java tricks to make quicksort even more. So they cut off at a certain point. Remember, shell sort also did that, the one you had to go read up on your own. Shell sort also did that when my partitions get too small, rather than making another recursive form, another recursive form, another recursive form. If my partition is small enough, just insert and sort it. That is one of the tricks to change the code. And then the rest you don't have to know, but it's interesting to read through it, but it won't be in the test. So on a Sunday afternoon, when you're feeling blue, or over the Easter weekend when everybody went away and nobody asked you to go, read through this. Okay? Or go with them and take your book anyway. It's impressive. The rest of it is called the median of free partitioning and the entropy optimal sorting. We will talk about 3-way partitioning for quicksort throughout the book. So read it for interest's sake, but I won't ask things about it in the text. And the other way, yeah, okay, that's it. That's quicksort. So quicksort, very easy. Choose a pivot, assume I'm random. Choose a pivot which might as well, because the elements are random, the element AL0, A low. And then compare the value of A low. Store the value of A low from the left and from the right. And do a few exchanges. The exchange is marked in the main loop. It's outside. And go through that loop. Okay. If you get stuck on the maths, either memorize it and prove, or ask again. Work through the right output proofs, look at the point where you get stuck and ask you. Okay? Everybody happy? Enjoy. And tomorrow is the cut. The week after that is the test, so the cuts are not compulsory, it's up to you, but you must get some blood. Thank you very much.